Okay, the first exercise I want to do now, after we have installed the Anaconda, Jupyter Notebook, HFSS, and Qiskit Metal, I want to show you is to how to do the so-called eigenmode and EPR, energy participation ratio analysis. This is important because you can use the EPR then to calculate the cross cut, which will which will tell you how much a qubit is going to change the resonance frequency of a cavity, and that can be used to for us to read out a superconductor qubit. The example I'm showing here is the tutorial in Qiskit Metal. After this tutorial, I will then show you how to do a 3D cavity one. We will still use a similar framework, but we are not going to use Qiskit Metal to draw the layout. We will directly use HFSS. Okay, so let's start. I start the Anaconda like what we did last time, right? Last time I already create an environment, so I'm going to activate it. It is called Q Metal. This is the environment in which I installed the Pi EPR, and then I just start Jupyter Notebook. And this will begin, and then I go to my directory. I already downloaded this notebook, right? You can download yourself. And this is the eigenmode and EPR analysis. We only will go through some of them, okay? So just click your mouse in one of the cells, shift enter, then you will run it. These are some description. The first thing is going to load the library that is necessary. I'm not going to explain them. You can read it yourself. And then it will start create a chip with this dimension. This is a superconducting qubit chip, expect to be 2 millimeter by 2 millimeter. Okay, and then it will start, and you see that here it pop up the Qiskit Metal interface, right? And it will start create some of the device. Like here, this is a Transmon Qubit with a capacitor, and this is the readout, and the middle one is just a metal to represent the superconducting qubit, the Josephson junction. Okay, we'll discuss more later. And then it imports the energy participation ratio analysis EPR, right? And then it just set up different things. Again, I won't go into details. Shift enter, and you see that it's going to tell you what it has. It has set up some of the parameter. I will explain a little bit more, but particularly we are not simulating superconducting device or the Josephson junction in HFSS. It cannot do that. But we assume that it has an effective inductance. This is the Josephson junction inductance of 11 nanohenry. And this is very important. Okay. Then we run the simulation. Now, the point is this. Here you created the layout, right? You can do many things to create a layout. But then when you run the simulation, it will bring up the HFSS. Now look at this. It created a structure. Look at this structure. It is a 3D structure, although basically the circuit is a 2D plane, right? So after that, then you will run the simulation. So let me do it. Explain a little bit about this Josephson junction qubit. So I can click on this screen. Control plus, then I can zoom in, right? Now, so I actually say something not very correct. Oh, I think it's still correct if I call this Transmon. So this is the mostly the capacitors. You can say this is a shunt capacitor, but this is also the terminals of the superconducting qubit, the Josephson junction. And where is the junction? The junction is supposed to be an aluminum oxide and then sandwich by 2 niobium, right? Usually, which are the superconductor. But here we just replace it with a metal plate. Let's take a look what it is. If I click on this, actually difficult to click. I need to move it so I see this pink square. Then I can click on it. Then I selected this, right? So if you see that, you see this is actually a sheet of square, and it has been assigned to a lump RLC boundary condition. If you click on this, you see that it say that I try to have it is going to assign it with a parallel inductance of 10 nanohenry. This is very huge. Any one of you have done RF design, you know that to get 10 nanohenry, usually you need to have maybe I guess almost 500 micron by 500 micron area. But here, because we are using Josephson junction, right, you can try to measure the length. For example, I click on measure edge. You see that this edge is what? It's only 13 micron. Okay, so this is very small. Yeah, but I think that this 30 micron is still quite big for me. Actually, in reality, it should not be that big, 30 micron, right? But anyway, it represents the whole thing, this whole thing as a Josephson junction, right? And then outside we have this, now I should just go back, instead of doing measurement, I just type escape, right? And then just come here, right? I want to click on the object instead, right? So if I come here now, I click on this one, you see that it is a pad, right? And this one actually assign a boundary condition also. If I click on this perfect E, right? Let me zoom out by pressing Control Shift or Control minus. Click on here, Control minus, right? And then I click here to unselect them. These are all the superconductor, because we assign them as a perfect electric field condition. If you double click this is a perfect E field boundary condition, means that they are just superconductor, right? No resistivity. And here is the ground plane, and this is the capacitor. Because it's a transmon, so you have a Josephson junction and also a huge capacitor. Now, but anyway, this is how it set up the boundary condition. However, there is something I want to bring your attention to is this. It also create a line here. Do you see this pink line? This is just a line. It's useless in this simulation, but it is useful later when it passes the result back to this Qiskit Metal. It uses it to calculate how much energy or in the there inside the Josephson junction. And for this, they can use it to calculate the energy participation ratio. Right? This is just a brief overview. In the next video, we'll do a 3D cavity, and I will show you how to create this. Right? But if you are just creating a 2D circuit, then it is better to use Qiskit Metal. Okay. So once and by the way, and then it was running the simulation. As you can see now, I double click the mode, right, the results, and you can see that the at different passes, this is the pass after which it determines whether it is converged. Usually it determines that it is converged after the consecutive pass have a certain error smaller than a certain value, and this is set up in this analysis, right? So here it say that as long as first it said maximum you can only have 6 pass, and then if you converge earlier, then if the percentage difference is less than 0.4%, then you can converge. You no need to continue to do one more simulation. Now all these are set up in the Qiskit Metal. Okay, you see that when we do the setup here, we say setup data, right? You say I want to analyze 1 mole, maximum pass is 6, minimum pass is 1. So that's the good thing about Qiskit Metal. You can do everything here, right? Although now I'm doing this manually, but you basically don't need to look at this HFSS. Okay, and now then we will just get back some of the data. It will also take some screenshots, right? This is exactly the screenshot we are seeing now. Then you take it to this interface, and then it tells us the frequency in gigahertz as the number of pass. We just take the data from HFS, so nothing special, right? Now, the important thing is that now it will start doing the eigenmode analysis, right? So let's just wait. It will take some time. Okay, so you get this, and then it also plot the distribution of the electric field. Okay, so this is just to show you that you can just use Qiskit Metal to build your Transmon, right? As what you seen earlier in another video, or just download the tutorial from Qiskit. You can build your circuit. But here, after you build your circuit, you send it to the HFSS, and it does the eigenmode simulation for you, and then also it can do the energy calculation and to do something useful for the superconducting qubit design. Okay, now, so after it done the simulation, we can do something called EPR analysis, energy participation ratio. Now, so from here you see that it does require two important quantity. One is the 9. This is the JJLJQ1 red JJ underscore, right? This is exactly the 9, right? I click on this and say fit selector. This is the 9 at the Josephson junction that we are trying to simulate, right? So I say that the whole Josephson junction is just modeled as a plate, a conductive plate, because we don't simulate the detail, and we cannot do that in HFSS. What we care is that it gives us a very huge inductance, which is 10 nanohenry, as we showed earlier. But we need to have this 9 because it's going to find the energy by integrating along this 9. So this 9 does not affect the simulation. It's for post-processing purpose. Another thing is that you also need to tell it which square is the Josephson junction, and this is the square, right? So this is JJ red all the way to underscore JJ, and you take a look, it is this one, right? So this basically tell Qiskit Metal that, okay, you run the simulation, and where is my Josephson junction? It is under this plate, and then it is it has this line for you to do the integration. Okay, so after we set up this, then again you put in the box and then shift enter, right? Then you ask it to do the EPR analysis. Let's see what it does. Now, we only simulate one mode, right? Number of mode is determined in your setup. As I said earlier, you put the mode, you say number of mode equal to 1. You only look at the fundamental mode of this system, right? So it's going to analyze this mode, and we calculated it is 6.22 gigahertz for that mode. Now, here it tells you how much energy is inside the Josephson junction, right? And basically, here you say that about 90% of them are in the Josephson junction, okay? Now, with this, then it will do the so-called energy participation ratio analysis to find the so-called cross curve. But here we cannot find that actually. We cannot find the cross curve, but it finished the energy participation ratio analysis. So this is a very brief introduction, and I will not go to the bottom like the coplanar waveguide resonator, right? Because this is only what I'm doing just now is only the Josephson junction. Okay, but maybe I should actually keep going. We done the just done the Transmon itself, okay? And now we will try to build a coplanar waveguide and then understand how that resonator behave, right? So I just keep typing, and you do see that here it start adding the coplanar waveguide, which will add as the resonator, a cavity, okay? So now you have an artificial atom, right, as we will learn in the class, and also a cavity. So you form an artificial atom and cavity. They will share the energy and they will affect each other, okay? And then, of course, then it will be passed to the Qiskit Metal to run the simulation, right? But obviously, you see that it create a new structure, and this is the coplanar waveguide. You type shift and then drag your mouse, then it will move around. Control plus, you will zoom in. Okay, so let's look at this, right? And you have this. It is actually necessary in reality to avoid spurious solution, to have an equalized potential. I won't go into details in this, but this is something it generates automatically. Okay, so here it does the analysis. So it found that the resonant frequency is about 9.6 gigahertz. Remember what is the resonance the mode of the Josephson junction? It is about 6, right? Where's that? Here, right? Not 6, it's about 5.8 gigahertz, right? And then the resonator itself, it is about 9.6 gigahertz, okay? So then this is good, right? So we have this system, and here shows the electric field distribution. You can go through them, and then eventually we come to the EPR analysis, right? So what we want to see is, with this qubit, how is it going to change the resonance frequency of the cavity? And when the qubit is up and down, the effect will be approximately equal to the so-called cross curve. It's going to change the resonator frequency differently so that we can measure whether a qubit is in up or down state, right? So let's just follow this. We just shift enter, go through all of them. Again, they are creating all the circuits, right? If you don't trust me, then we just come here and wait. Looks like this got frozen. Okay, but right, so now you see that it is creating the system, right? Now you have the resonator and you also have the qubit, okay? And now it is doing the eigenmode analysis. As you can see here, it is eigenmode on the left, right? It is doing the eigenmode analysis. Transmon and resonator. And after it finishes, it will plot the result. So while it is running, I will go back to this one. Got frozen. I don't know why. Let's go back to the notebook, right? So after it done all this thing, then we will perform something called EPR analysis, and that's why remember, it is important to identify which one is the rectangle associated with the qubit and the 9 you want to use for integration. Okay, so I just do this, and let's just wait. It will take some time, but since this is essentially 2D, now you look at this. Look at the frequency versus the this is the mode, right? The frequency versus the path, right? So we want to see the last. The first mode is about 6 something, right? So if I right click, marker, add marker, then I click on here, it's about 6 gigahertz, right? And then the second one, which is the resonator, is about 9, right? It is not the same as before. That is because now you have a new system. They couple to each other, right? So this is good, right? We have done this. And now if we come back to here, you see that it is working very hard to do something called EPR analysis, just like what I showed you before, because now it has 2 mode. The first mode, you do have 99% of the energy at the Josephson junction, but the second mode, you only have a 0.3% of energy at the junction, because this mode is mostly the cavity mode, the mode due to the resonator, right? And then you can do an EPR analysis. Now you see this one. This is the so-called cross curve. It basically tells you that with this Josephson junction or this Transmon Qubit, you are going to modify the resonator frequency, right? The resonance frequency of the resonator or the coplanar waveguide by about 2.3 megahertz. Now think about it, the original frequency, right? Remember, is about 9.9 gigahertz. By adding the qubit, whether it's spin up or spin down, it will change it, so the difference is about 2.5 megahertz less, right? So this is about 1/3000 of the frequency, very tiny, but that is enough for us to detect the qubit, whether it is up or down, 0 or 1. Okay, so this is the something I would like you to go over, play with it, and then next video we will talk about how to create a 3D cavity. And after you okay, that's I press it too much. Right after that, you will find that you cannot close this answers, because if I try to close it, it says it's being used. Right, to gracefully close it, you want to use this function to say this one sim.close, right? Close all of them, and then now I should be able to close it, right? You can save it, or you can just say you don't save it, right? I don't need to save, I just say no.